So today we're going to continue working with classification trees, but we're going to make things more complicated this time around, okay? Now, first of all, I'd like to point out this consideration. The only classification tree that we did so far was fairly useless, right? It was about predicting on Titanic among the passengers who will die and who will survive, right? What's the value of this prediction? Nothing really, okay? It's all water under the bridge anyway, right? So, but we used that example as the training ground to see what classification tree is and how it is constructed, right? Now, what you didn't realize maybe is that in our Titanic classification tree, the target was the column survived, right? And it was a categorical target, right? Because the possible responses are yes or no. That's why we built classification tree and not regression model, okay? But what you probably didn't realize is that all of our predictors were categorical as well. We had three predictors, right? One of them was age, and instead of a number, it was adult or a child, a classification, right? So it's a categorical predictor. Another predictor was gender, right? Male, female. It's also a categorical variable. And another predictor was class, right? They could travel first class, second class, third, or they were part of the crew. Not a number, it's a categorical predictor. So all of our predictors were categorical, okay? We may have cases, and we will have cases, when our predictors are not necessarily categorical. They can be not categorical, then what? Ordinary is also categorical. Numerical, right? So, for that, let's take a look at a great example, which I totally made up. So, go to Scholar, and in the folder Data Files, over there, you should see the file which I posted today called mowers.csv. Now you know what to do, right? You need to download this file, and after that, take it from the downloads folder and move it where? To the data folder, right? Disk C, folder data, okay? So I already did that, so I'm not going to download the file and move it, all right? But you go ahead and do that. Download the file and go to the folder, downloads, select the file, copy, paste it into the C data folder. Because that's where we agreed to put everything that we're going to analyze, right? Okay. Are you there yet? Is there anybody who doesn't know how to move the file from one folder to another folder yet? It should be very straightforward, right? It should be very simple. Okay, so let's go ahead and analyze this data. So I'm going to start our studio, and you do the same, okay? All right. Oh yeah, and I need to make it bigger, right? So let's do that. All right, so I'm going to start a new window. You know how to do that, right? New script. You just click on the plus sign in the upper left corner and say new R script. And that will create a blank script for you. By the way, the script that we did last class is posted online, so everything I uploaded to Scholar. If you download, you will see pretty much all the steps that we did, okay? All right, so let's take a look at the file, okay? What's the very first step that I always do before I start messing with data? Yeah, import the data from the CSV file, right? Okay, so I'm going to call my data in the memory mowers_data. Simple as that. Oops, mowers_data. And that, whoops, I can use equal sign. We discussed it, right? So instead of this arrow, less than dash, I can just go ahead and say equal is the same thing, okay? So mowers data is, what function do I use? read.csv, right? I need to read from the CSV file, and then in quotation marks, I have to specify full path to the file. So disk C folder data file is called mowers.csv. Okay? All parts and pieces of this statement are important. And when I run it, it should have no objections, no red stuff. Okay? Everybody is cool? Yeah. Read.csv, and then the file location. If you're on Mac, there is no C drive on the Mac, right? There is only slash, and then the folder, and then the file name. Okay. So Mac file system is different from PC file system. Is everybody okay? Read the data? Okay, cool. Well, let's take a look at the data structure. It's typically a good idea, right, to see what's inside. So str structure, right? Str of my file mowers underscore data, just like that. Okay, so I'm going to hit run, and look what happens. Okay, it's teeny tiny data. Okay, microscopic data. It has only 24 lines, right? So in this file, I have information. I have data on 24 people who are either owners, excuse me, of the lawnmowers, or they are not owners. Okay. So who might be interested in data like this? Which people have lawnmowers and which people don't have lawnmowers? Retailers, such as, I don't know, Lowe's, Home Depot, right? They want to find out what's the typical profile of the customer who will likely buy a lawnmower. All right. Okay. So in other words, this last column, ownership, is going to be my what? Target variable. Exactly right. It's going to be my target variable. Right? I'm going to try to predict which kind of people will buy the lawnmower and not buy the lawnmower. Okay. And therefore, columns income and lot size are going to be my predictors. Right? Now, note that ownership, even though it's classified as an integer, it's really 0 and 1. Okay, so 0 means no, 1 means yes. On the other hand, my predictors, income and lot size, are both numerical, right? 60, 85.5, I'm guessing that's thousands of dollars. Okay, and the lot size 18.4, 16.8, whatever the units are, I don't know. Probably not acres, right? Because it's just a lot of land, basically. Okay, so what I'm going to do is try to build same thing, classification tree, that will hopefully allow me to predict who will buy or not buy lawnmower based on their income level and the lot size. Now, if you would have to guess, lot size, what's the general rule could be? Bigger lot size, you'll likely buy the lawnmower. Smaller lot size, probably not, right? Same with income, I'm guessing, right? Because lawnmowers, from what I hear, are not cheap things, right? Especially professional ones, okay? But, you know, we'll let the chips fall where they may, and let's create the classification tree. So, first thing that I need to do is what? Import the library that will allow me to create the tree. What library is that? R part, recursive partitioning. So I'm going to say, well, let's bring the library R part. Bam. If I'm running that, it says warning. Yeah, that's fine. Okay. So after that, I'm going to do the tree model, right? So mowers underscore classification underscore tree underscore model, and in there I need to record the result of the function rPart, and three things I need to specify for the function, right? First, what is my target and what are my predictors? Well, my target is, well, from what I can see, column titled ownership, lowercase o, mind you, okay, ownership, and then I have to put the tilde sign, meaning that this was my target, and what's about to happen are my predictors. Remember how I avoid typing the names of predictors, but kind of say all of them? Period, right? So I need to put dot, and that's it pretty much, right? Let's show. And then I have comma, so this is the first thing, right? My target is ownership versus everything else as a bunch of predictors. Then I have to say what data to use. Well, data is what I just read from the file, right? So data equals mowers underscore data, okay? And the last one is this algorithm, which is called CART, classification and regression trees, right? It can do both classification trees and it can do the regression trees, something that we didn't discuss yet, but we will next week. This one is what? What's the type of my target? No, not quite. Not the regression, the classification. My target is 0, 1. 0 means no, 1 means yes. It's a categorical variable. Okay, so therefore I'm using classification tree, right? So I'm going to have to say method to use is quote unquote class, meaning classification. My target is categorical. Okay, so I'm going to run the line, and after that I want to show the result of my tree, right? The resulting tree. So for that I need to bring in what library? rpart.plot, right? rpart creates the tree for you. rpart.plot plots the tree for you. Okay, so rpart.plot, and then after that rpart.plot, and here I need to insert the name of my model, which is mowers, really long name, but this is it, right? Okay. So after that I'm going to run the model, and there it is. This is my tree. Not very sophisticated tree, which is fine, right? It was very small data to begin with, so what do you expect? You have 24 observations, right? It's really small data, so tree is not going to be very sophisticated, okay? So how do, everybody got the tree? Yay? Are we good? Uh-huh. rplot? Well, so that I can use the rplot function to do that. Okay? So it's a way for me to bring a picture of the tree. So I need to bring, and you know what to do if some of these libraries don't show up on your machine, right? You need to install the package, right? And install the package, you can either type the line, install.packages, and then name of the package, or you can simply go here, say packages, install, and type the name. Yeah. So essentially what I did is I started the RStudio from, like, it was not running, right? I started the RStudio, so I have to bring the library into the memory. So it should be part of the code at least once. Okay? Okay, so let's take a look at, oh God, where did it go? Plots, right? Yeah. Let's take a look at the tree. Very simple tree, right? And remember, the rule is every node, so this becomes my root node and also the decision node at the same time, right? The very first variable where it says we need to split, and the only in fact split, okay, is based on income, and income is $60,000. Yes, you go to the left, no, you go to the right, okay? So here is the test, right, for us, how to use this tree essentially. A person comes in, or, you know, we're deciding, for example, let's say I'm Home Depot, okay, who is trying to decide, I'm the marketing manager, trying to decide who would be the customers that will receive a new, what's it called, coupon, right, or special, you know, kind of a postcard in their mail, right? One thing that I can do is just basically carpet bomb, right? Send it to everybody in the area. Well, that would be kind of a little stupid, okay? Why? Because some people don't have enough income, right? Some people don't have big enough lot. Some people live in the apartment buildings, and you don't need lawn mower. when you're renting, right, in an apartment building. So therefore, instead of that, instead of spending thousands and thousands of dollars, I can go ahead and use that type of analysis to decide what to do in my target group, right? So it appears that the only reasonable, the only viable test that I have to do to decide is look at the income, right? If people have less than $60,000 income, then I go to the left, and here is my node, okay? So are these buyers or non-buyers? Tell me. Non-buyers, right? Because what's reported over here, first of all, there are 33% of people like that. That's what it says, right? 100% of your data, all 24 observations, okay, are split, roughly speaking, 1/3 or 8 observations are people below $60,000, and 2/3, 67% people above $60,000, right? So, we discussed that this fraction represents the percentage of people responding yes or one, right? Because it's the same thing, yes and one. So in our case, one means yes, right? So therefore, percentage of owners among people with less than $60,000 income is 0.12. And then the rule of 0.5 kicks in, right? Default cutoff probability used by classification trees is 0.5. Whichever proportion is higher than 0.5, that's how we classify the entire node. So in this node, people less than $60,000 per year, percentage of yeses is 12, percentage of no's is 88, 88 is more than 0.5, hence we classify this entire node as no, as 0, right? On the other hand, if your income is above $60,000, and we go this way, right, then 69% of these people are ones. That means that they do have a lone mover, right? So hence, everybody who is in this node, we're classifying as a yes, as a one, right? Well, this is our target audience, essentially, all people with incomes more than $60,000, okay? So the reason why I wanted to bring this up, this simple example, is to contrast with what we did before in the previous week, right? In the Titanic example, all of our predictors are categorical. In this example, all of our predictors are numerical. Yes, sir? Oh, it's apples and oranges. 33% means what? This 33%, what does it mean? Of the data set, right? So 33% of the data is in this node right here, okay? So out of 24 observations, 8 ended up in this node. 0.12 means among these people who are in this node, 12% are the owners. So essentially it's like 1 out of all 8 of them, right? That's what it is. Okay? So first number, lower number is what percentage of the entire data set is included there. And this one is what is the proportion of yeses or ones. Okay? All right, so let me give you quick insight into how the algorithm works. It's actually pretty amazing. Okay, here's what the algorithm does. When we start at the root node, the algorithm says, okay, we have two variables, right? Well, let's start with incomes, for example. Incomes in my file, I don't know what. I believe the highest income was. Oh God, I can't remember. What the highest income was $110,000. Lowest was like $30-something thousand. Okay, and this is what the algorithm does. It says, let's take a look at all possible ways how we can split the data set into set 1 and set 2. Okay, so let's say, for example, just for the argument's sake, 30 is our lowest income. And then next one is 33.5, and the next one is 41.2, etc. Okay, last one is $110,000. What algorithm does essentially is it says, let's try every possible split. In other words, my first split is going to be like this. Below 33.5 and above. Okay, so there's going to be only one observation here, right? And there's going to be the rest of them 21 observations here, okay? And what the algorithm is going to look for, remember how the classification tree works? What's the goal? the goal is for the leaves, right? These are terminal leaves right here, right? These are terminal leaves. The goal is for the terminal leaves to be as pure as possible, right? That means that preferably they should contain only one type of response, right? If I have a mixture, the more mixture I have, the worse it is, right? The worst case is 50-50. Half yeses and half no's. Doesn't give me any information who are they, right? Half and half. No data, no info, okay? The best case scenario is everything is 1 and nothing is 0, or nothing is 1, everything is 0, right? That's the best thing. So we try split like this first. After that it says, okay, let's try another split, okay? And another split is going to be 41.2, less than 41.2, so I'm going to end up with 2 observations here, right? And 22 observations here, okay? Then the algorithm will look how pure the resulting nodes are, okay? And the next one is going to be, let's say, just for the argument's sake, okay? Just for the argument's sake, that the next one is $53,000. Next, it will try to split on $53,000. So 3 observations are going to be here, and 21 observations is going to be here. It will again evaluate how pure the resulting sets are. So it will literally try every single possible split value. And it will pick the one that fits the profile the best. Right? What I mean by that is the pure separation of yeses and no's in each of the resulting 2 subsets. Oh yeah, and by the way, this is just splitting on income, right? What about the lot size? Same thing actually, okay? So it will try to split on each possible value of income, and after that it will try to split on each single possible value of lot size, okay? So we have 24 incomes, we have 24 lot sizes, so it will try splitting in about, 45, 46 different ways, okay? And out of these possible splits, it will pick the one that gives you the cleanest separation of yeses from no's in both resulting subset 1 and subset 2, okay? So it's a lot of work going on behind the scenes, okay? We don't see any of that, of course, right? Software does that without us seeing it, but that's essentially what we're looking at, okay? We're looking at out of all the possible splits on income, and out of all possible splits on possible lot sizes, the software found that the best way to split the data set would be based on income. Not only just any income. The best value of split would be less than 60 versus greater than 60, okay? And after that, remember how we discussed that the R part, why is it called R part? Recursive partition, right? We can split further, technically, but the algorithm decided not to do it. Why? Because it found that even though we can keep splitting, right? We can keep splitting on different level of income, on the lot size, right? So splits are possible. It decided not to do it. Why? Because apparently no further splits result in a cleaner subset. Okay? So the idea is not to split it until the hell freezes over. The idea is to keep splitting until you can get separation yeses and no's, right? Once there is no further improvement, no cleaner separation of yeses from no's, that's where the algorithm stops and says, yep, this is it pretty much, okay? Make sense? All right. Well, ladies and gentlemen, let's mix it up, okay? Let's create another classification tree using yet another and more realistic example, okay? So I'm going to assume that you have no questions. All right. Go back to Scholar, please, and download yet another file that I posted today called bank.csv. Okay, so we're going to take a look at the financial example. Well, it's kind of marketing, a real example, not as much financial, okay, as it is marketing. All right, so same thing, right? Click download. The file lands in your downloads folder. Then take it from downloads folder, move it to see this folder data. Okay. All right. So let's start slicing and dicing this one. Okay. So what I'm going to do is, we're pretty much done with this example. Do you want me to post this script, by the way? I mean, it's not much. I can post it. Okay. So I'm going to create a new R script. And again, what's the first thing that we do before messing with data? Import that from CSV file, right? That's step one. I'm not going to put comments anymore, okay? At least here, at this stage, okay? I'm going to assume that we did already importing the file 2 or 3, 4 times, and by now you got used to the idea that the very first thing that you always do is you bring the data into the memory, you read it, okay? Simple as that. So I'm going to say bank data, bank underscore data, and that is read.csv file from disk C, folder data, file is called bank.csv. Don't forget .csv. If you do, it will not like it. Okay? Alright, so let's investigate what's inside. str, structure of bank data. Bam. Okay? Same thing. Alright, so now I have actually a more sophisticated data set, right? Let me tell you what's inside. First of all, you tell me, how many observations or customers do I have? 5,000 customers. And about each customer, I know 12 things, right? 12 variables, okay? Thing number 1, personal loan. And you can see that the possible answers are yes or a no, okay? So, let me give you a little bit background behind this file. The idea here is that the bank, you know how banks make money, right? They make money by lending money to customers, right? And charging them interest. That's in a nutshell the nature of their business, okay? So, how many of you received in the mail proposal or letter or postcard from your bank saying, yes, we have really cool credit card or, you know, mortgages. You can apply for the mortgage at only 3.125%. Probably everybody in their lifetime received that kind of mail at least once, right? Okay, so why banks do that? Because, well, they hope that you receive this card in the mail, right? Then you say, oh my God, look at that. They're financing, they're giving the auto loans, and there is this Lexus that I always wanted. So let me go get an auto loan from them and buy this Lex, okay? So they hope that customers, at least some of them, right, receive this thing, apply for the loan, get the money from the bank, and start paying this off. What do you think happens with the majority of these envelopes? Throw away, right? They go to the trash, right? Quite high percentage, probably. But in some small percentages, they customers, you know, they're like, yeah, okay, I'm interested. Let me call them, and maybe it will result in the loan, right? So from the bank standpoint, it's actually beneficial to have a target advertising, right? Just like with loan mortgage, okay? What does that mean? Well, they can again carpet bomb the entire area and send letters to everybody, right? Hoping that some people will get a loan from them. But it's a better idea to identify customers or customer groups who are most likely to apply for the loan when they receive an invitation, right? Unsolicited invitation. And make them as the primary focus of the advertising, okay? So this is my target, personal loan, okay? So out of these 8,000 observations, some people said yes, and some people said no. So essentially this is historical data, right? The bank took 5,000 customers, and mailed them an unsolicited offer. Do you want to get a loan from me? And those people who came back and applied, they labeled as 1. They did apply. Okay? Now, whether or not it was successful, different thing, right? What they want is an application for a loan from you, okay? So, small portion of these 5,000 customers came back and they labeled them as 1. The rest of them they never heard from, and they labeled them as zeros, right? We mailed something, nothing happened after that, okay? So this is my target variable. What type of the target is that? Some people agreed to a loan, said yes, we'll label them as 1. Some people didn't, and we'll label them no, 0. That would be categorical. So therefore, immediately I know that I'm talking about classification model, right? Okay, let's take a look at predictors. Age. Age is a numerical predictor, you can see, right? That's a real, actual age in terms of years. Okay. Experience years. I guess that means how many years you've been with your last employer or just generally employed, right? Whatever it is. Also years, numerical predictor. Income. My guess would be that its income is listed in thousands of dollars. That would be my guess, right? Also numerical predictor, right? Family size. 4 people, 3 people, 1, 2, numerical, right? CC average balance, that would be credit card average balance, right? Your average monthly balance of your credit card statement. Also number, right? Education, BS, doctorate, and it says 3 levels. What's the other one? What do you think? BS stands for Bachelor of Science. Doctorate, well, that's doctorate. And what's the other one? MS, Masters, right? Why is it listed BS, doctorate, MS? Alphabetical, right? I told you that before, and you remember that? Good. So categorical things that we can put, that have a string attached to the title, right? Not to the title, to different levels, different categories. They're listed in an alphabetical order. So this is my categorical predictor. Okay. Mortgage balance. If the mortgage is held by this bank, right? 0 means there is no mortgage. This customer has no mortgage with us. This customer, though, on the other hand, has $155,000 still remaining on the mortgage balance, right? Okay, numerical, obviously. Securities account. Yes, no. Does this customer have the securities account with us? What do we mean by securities account? Well, like say, for example, you're trading stocks, right? Oopsie. So sometimes you buy stocks, sometimes you sell stocks. For that, you need to open a securities account with the bank, right? Such as Merrill Lynch is the branch of Bank of America, right? You open the securities account, you trade for Merrill Lynch. Okay, CD account, certificate of deposit, right? So it's a kind of medium-term deposit, right? You're not allowed to touch this money until a certain date, right? In exchange, you get small, teeny tiny percentage out of bank, right? Online banking, some people do online banking, some people don't. Yes, no, right? And then credit card. Does this customer hold credit card with us? Yes or no? So all of these things, securities account, CD, online banking, and credit card, because they're yeses and nos, these are categorical predictors, right? So you see what I have here is a mixed bag of variables, of predictors. Some of them are numerical, right? Age, credit card balance, experience, number of family members, and some of them are categorical. See, this is kind of a, it's more realistic example. The ones that we looked before at, Titanic, everything was categorical, right? Lawnmowers, everything was numerical predictors. Now we have a mixed bag. Okay, now what we're going to do today is this. Very important topic in the whole data analytics. Let me ask you this question, true or false? The bigger is my tree, that means it has a lot of branches, kind of keeps splitting down further and further and further on a lot of different variables. The more detailed the tree becomes, the more aspects of reality the tree captures, therefore the more accurate the predictions are becoming. True? You would think so. And that actually is true, okay? But here is the downside of this, okay? I can build tree as detailed as possible. You know what? If I allow the tree to grow infinitely large to the extent that in each terminal leaf, in each last terminal node, I can have as little as only one observation. If I keep splitting tree further and further and further, I will arrive to a perfect tree. It will have 100% accuracy. If need to be, right? Because I can basically separate observations so finely, okay, on such a fine level that each final terminal node will contain only a handful, maybe even one only observation. And you understand that if one observation is in the final terminal node, it's pure node, right? It's 100% yes or 100% no. There is nothing else can happen, right? So if I allow the tree to grow infinitely deep, okay, as deep as it can, then I will eventually arrive to a perfect classification model. Is that a good thing or is it a bad thing? It's actually a bad thing. You would think it's good, right? 100% accuracy. I mean, it's beautiful, right? No. Here's the reason, okay? Let's kind of discuss the lawn mowers or even that one, okay? This example. True or false? Humans are not perfectly rational creatures. True. Sometimes you make decisions that are kind of on the spur of the moment, right? You want to check out the nearest dealership, you may be thinking about the car, right? Buying a new car. You came to the dealership without, thinking that you will buy the car today, and then you saw this car, it's shiny, it has this cool black color, right? Chrome parts, this new car smell, and you're like, yeah, we live only once, let's buy it today, right? Bam. Didn't plan on that, and here you are with a new car, minus $25,000. Okay, happens, right? Or you go to the checkout counter and you're looking on the side, and there is this national what is it called? National Enquirer, the journals about celebrities. People magazine, right? Somebody gets divorced, somebody gets pregnant. And, Angelina Jolie and Brad Pitt are splitting up, shocking revelations, so all this stuff, and you're like, oh my God, this is interesting, let me buy it, right? It's a decision on the spur of the moment, right? Lawn mower, you have like small land plot, right? You don't have much income, but, your dad taught you how to fix lawn mowers, and you have this, love for the lawn mowers. You like to do things by hand, right? You're saying, what the hell, let's buy the lawnmower after all, right? So I like them, why not? Okay, so you make a rational decision which is not justified, strictly speaking, but you do it anyway, right? So my question to you is, do we want to build a classification tree that captures these types of decisions? Random, on the spur of the moment, irrational decisions? Probably not, right? We want to capture the important parts of the data, something that's called sometimes signal versus noise, okay? Signal is the main thing. That means that if I take, let's say, 5,000 observations like this, okay, and I analyze it, and I take different data set, 5,000 different observations, I will see same trends in general, okay? People, for example, with high incomes are more inclined to agree to a loan, right? People with larger families are more inclined to agree to the loan, right? People with, let's say, higher education levels are more likely. Something like this that is repeatable, right? I can analyze different data sets and I'll see, generally speaking, same stuff, okay? As opposed to noise. Noise is randomness, okay? I just happen to have these 5,000 observations, and among them, I don't know, some people with small income and, high credit card balance or low credit card balance, they still apply to the credit card because they thought, why not? Let's do it, okay? So randomness, which is just built into this specific data set, that is something that I want to avoid, okay? So hence, ladies and gentlemen, let's discuss the concept of overfitting, really important concept in data analytics, okay? So here is, generally speaking, how data analytics is done, okay? Building of the models. Usually, people building data models, they don't use all of their data to create a model. Okay, so therefore, here's what normally happens, and this is what we're going to do next. I don't know, maybe not today. We'll see. Okay, I'm going to take my all data set, all records, the entire data set, and I'm going to split them unevenly between two subsets. Okay, subset number one. Now, from now on, let's make this pact agreement. Okay, we're never going to say build the model. We're going to say train the model. Okay? Building and training the model is the same thing. So subset number one is a set of records which I'm using to build or train my model. Hence, it's called training set. Training, that's an ugly T, okay. Training set, okay. So I'm using training set to create a model, okay, to build this tree structure, okay. And then after that, I'm going to see if the data, if my tree, if my model performs nicely on data that it did not see before. Okay, so in other words, what I want to see is kind of verify if my model is good enough, so that if I apply it to the data that I didn't use for training, some data that it doesn't know even exists, it still will give me good performance characteristics. So far we discussed two performance characteristics, right? What are they? Accuracy and closely related to accuracy, which is called misclassification rate, right? Okay, so therefore, I'm going to hold another data set. Oh, that's an ugly box. Okay, let me maybe, yeah, like this, okay? It's also called validation set. It's a validation set. Oops, validation. Or sometimes it's called hold out set, okay? So essentially, here's what I'm going to do. And typically, the split is uneven, okay? Training set normally contains anywhere between 70 to 80% of data. Now, when I say normally, that doesn't mean that it's always like that, okay? You can split it 60-40, okay? Or you can split it 90-10. But normally it's between 70 to 80% of data, therefore this one is going to hold the remaining, right? So between 10 to 20%, okay, of the data. Oops. Okay? Oh, sorry. 20 to 30, right? 20 to 30% of the data. Okay. So it's not unusual to see split 75% in your training set versus 25% in your validation set. It's fairly normal, okay? Or 80% versus 20%, okay? So the reason for that is this. I'm going to take my training set and use that to build my model. And again, we're not going to use the word build, we're going to use the word train, hence training set. After that, I'm going to take my model and apply it to the validation set just to make sure that my model performs well also on the validation set, right? So, in other words, the model generalizes well. Okay, I'm going to use this awkward word. Generalizes means that it's good enough to handle data that we use for training purposes and the data we didn't use for training purposes, something that the model never seen before. Okay, so that if I apply it to an unknown, unseen before data set, it will still give me decent performance. Okay. And here is basically the idea, okay? Remember our discussion today that you can keep splitting the tree more and more and more until it perfectly classifies everything, right? But that's kind of bad because you will capture this signal, the main features, okay? Why the data behaves the way it does. Plus the noise, right? Randomness that is specific to your training set, okay? So, in other words, here's what's going to happen. All right. So here, horizontally, I'm going to have number of splits. How many times my tree splits, okay? In other words, how detailed the tree is, right? The more it splits, the more details you capture, right? And vertically, I'm going to plot accuracy or misclassification. Let me plot the other one, misclassification rate. Misclassification rate. So, let me use two different colors. Let's see if I can bring a different color. Oh my god. Can I? No, doesn't look like I can. Okay. So, true or false? If my tree is kind of small and shallow, doesn't have a lot of splits, probably its accuracy not very high. right? Therefore, it has high error rate, misclassification rate, right? So, therefore, the tree starts over here, right? Small number of splits, not very good accuracy, high misclassification, a lot of errors, right? As I'm building my tree better and better and bigger, right, it will capture more and more different special cases, right? And therefore, the accuracy will become higher and higher, right? So therefore, I can expect something like this on my training set, okay? So this is how the misclassification behaves on the training set itself, okay? In other words, the bigger tree I'm building, the bigger tree I'm training, the more cases it starts to capture, therefore it classifies higher and higher percentage of cases correctly. The error goes down, okay? But here is the thing. At some point in time, if I take this tree and I apply it to my validation set, the accuracy or misclassification rate on my validation set is going to go down, but at some point it will actually start rising. Okay, so this is what happens. Whoa. This is what happens on my validation set. Why do you think it will happen? Why the tree will make less errors initially, and then errors will start creeping in? Because of the noise. Okay? Because my noise in the training set is different from the noise in the validation set. Okay? Noise is random stuff, right? That means nobody really knows how that happens or why that happens. So if I'm building bigger and bigger tree, I'm really trying to capture the noise in the training set. When I apply this model to my validation set, it will have different noise, right? So therefore, I'm going to actually make more errors because noises are different, right, in my training and validation set, okay? So from that standpoint, I should stop building the tree probably right around here, okay? I'm going to say that up until now, I captured all the essential features, and from that point on, what I'm doing is capturing the noise, right? I'm trying to model the noise, which I don't want to capture at all. So this is the optimal tree size, okay? Optimal tree size. So anything above this optimal tree size is something that's called overfitting, okay? Overfitting. In other words, building too good of a model. You want to avoid that. The more detailed model you're building, the more you're approximating the noise and not the signal. You're doing too good of a job, okay? Your model overfits the data. It follows the data too closely. And at some point in time, you start following the noise and not the signal. And you don't want that, okay? You want to model the signal and not the noise, okay? So therefore, trees should go deep enough, but not too deep. In this case, you're capturing the main features of your data, and you're leaving outside the noise of it, okay? All right, so we're over time today. So I'm going to post the practice problem for the upcoming test, and on Wednesday, we'll finish up this example, okay?